Hello, wonderful people of the internet. Welcome back to another episode of Simuleos. I hope you guys are all having a wonderful day. So, bit of bookkeeping as always before getting started. Let's go ahead and open up XernalPP, and then we're just gonna hop into it. So, I hope you guys are all having a great day. So what are we gonna do? Let's go ahead and just do a little bit of bookkeeping, like I said we would. Okay, so I'm basically going to be doing 2-hour streams every evening this week from 6 to 8 p.m. Eastern. However, tomorrow will be the exception. I will not be streaming tomorrow simply because there is an event that I have to go to. And so no streaming tomorrow. So no streaming. Whoa, okay, let's pretend I can write tomorrow. Okay, hey Alexor, how are you? But after that, we will be basically doing streams every day. Like I said before, I am going to be transitioning to doing a lot more stream content, a lot more YouTube content, a lot more of just a lot of different stuff, starting probably next week. Next week is basically the start of the holiday week, you could say, for MIT. As such, I have a lot of days off, and also I will be taking some time off while I am transitioning out of the MIT job. So because of that, I should start to do some longer streams starting next week. Martin Den 41, thank you so much for coming in. How are you? So yeah, we're going to see how this goes. I'm actually a little bit worried about how next year is going to go, but we'll see. Good things, done some reading today on modular arithmetic and such things. Oh, we're going to do a lot of modular arithmetic today. Today is going to be an interesting day. I think that's it for bookkeeping. I don't really have too much more to do. So I'm going to go ahead and erase this, and we're going to talk about what we're going to do today, which is, well, I mean, as Alexor said, a lot of modular arithmetic. So let's talk about why. There is this thing that a lot of you guys know about, and that I talk about a lot, called the Fourier Transform. Now, here's the thing. The Fourier Transform is a very interesting concept. Hi, I'm going to document my code today. Oh yeah, super, yeah, good luck. Okay, so how exactly do we describe this Fourier transform? Whenever I talk about the Fourier transform, I usually just draw two different number lines, one here and one here. Well, not number lines, but two different graphs. And on this one, we have the time domain, and over here we have the frequency domain, okay? And this is some sort of amplitude over here. It doesn't really matter, amplitude. So if we have some sort of sine wave over here, something that looks like this, with some sort of frequency, the sine wave is sine of omega t. So over here then, what we'll see on the frequency space is a single peak at omega. So this is at omega, right? So the idea here is that if you're doing a Fourier transform, essentially what we're trying to do is we're trying to decompose all of the signals in frequency space or all the signals in the time domain over here into unique frequencies that you can see in frequency space. That's kind of the overall idea. That's the heart of the Fourier transform. It's what, whenever I describe Fourier transforms, I always have to think about what it is that they're trying to do. And then after that, I kind of think of how we're going to do the implementation. So this is done in a rather remarkable way with something known as a Fourier operator, which we're going to talk about in a bit. So I'll catch up with chat in just a second. So today we're actually going to talk about the Fourier operator, but not necessarily in the way that we typically talk about it. Instead, I want to talk about the Fourier operator in a discrete sense that is also not complex. So we're going to talk about something that are known as number theoretic transforms, or NTTs, which are DFTs, discrete Fourier transforms, done on, instead of a complex ring, just a modular ring. Like, you know, the ring, instead of going from, you know, real, imaginary, just goes something like 0, 1, 2, 3, 4, 5, 6, 7, and then it's just kind of a modular operation like this. So that's kind of what we're going to talk about today. Thank you. Have you solved the ray problem? I couldn't catch you for some time because of the courses. So that would mean that probably the last stream that you saw for mine was a few months ago for the ray tracing. I'm assuming the ray tracing videos for the MIT course 18S191 on computational thinking. So let me just go there really quick. Julia, programming language YouTube channel, and I will show you that also. I just realized that I need to do a few more things here really quick. There, here, 91,000 views. Of course it has 91,000 views. Okay, so let's do playlists probably. There should be a computational thinking course. And then the ray tracing one ended up with a few videos. Here would probably be the most prevalent. Here's the most related one. So this is the video for 3D ray tracing. Just driving to work, listening to your sultry voice. I miss ya. How are you, Mossbond? I hope you're having a great time. And yeah, I'm generally... Wait, going to work? Oh, yeah, okay, it is that time to go to work, yeah. But yeah, so if you wanted to call, I think... Okay, we can talk about it later, but send me a message on Slack or something and we can talk a little bit more. I don't want to, kind of unveil everyone's identity or whatever. But I hope you have fun at work. So anyway, for those who were asking about the ray tracing stuff, that was probably the last video I did on ray tracing. So yes, we did solve the ray tracing problem in that we were able to do both 2-dimensional and 3-dimensional ray tracing. See you, Mossbond. Have a wonderful day. So yeah, that problem solved. As far as the MIT course is concerned, I think maybe I should address that just a little bit before continuing on stream. Obviously, the MIT course is now over. If you guys did have the chance to catch the MIT course when it was live and you followed it, I would really appreciate if you could. And let me just do this really quick. Is this the screen I want? Wait. Yes, this is the screen I want. What is this screen? Okay, I'm sorry. I forgot my keybinds. Let me give you a link really quick for those of you guys who were following the MIT course. It is this link in here that I'm putting into chat. Let me go over. Wait. 1 second. I can't show my screen yet. Okay, so now I can show my screen. So if you guys did follow the course, please feel free to fill out this form. It is a feedback form for the MIT course here. And basically, like, the most interesting new idea, the most challenging part of the course, how the course could be improved, whether the format was actually useful for people, further comments, this kind of stuff would be really useful. So we're trying to collect some feedback and go from there. How come this guy has more views than you? I'm pretty sure you know who that guy is. That guy is 3 Blue 1 Brown. He's a he makes some amazing content on YouTube. So 3 Blue 1 Brown. Yeah, we've got a few ideas for videos that we could do together in the new year, but I don't want to spoil anything. So I'm not going to talk about it here on stream. Essentially, if I'm going to be doing a collaboration with someone, I'm hoping that you guys don't know it's a collaboration until the video comes out. So that's kind of my goal. But I do have a few collaborations with different YouTubers coming up, and I'm pretty excited for them, actually. Anyway, so this is that guy. This face, I'm only here for you. Thanks, Onidu. But yes, this guy is he's an amazing YouTuber. He does math visualizations and stuff, and so because of that, his videos tend to get a few more views. Plus, he does some amazing content. So that's why. However, as far as the course is concerned, I was actually genuinely happy with how the course turned out. Not necessarily because the whole time was, hunky-dory. There were a lot of situations, there were a lot of times when I was developing content for the course and I was quite frustrated. So yeah, it wasn't exactly, all fine and dandy, but what I will say is that the product that we put out at the end, I think, for the MIT course was pretty good. There were some issues that could have been solved and should be solved next time, but it was pretty good. Excellent YouTube channel. Also found Leos through him. Yeah, a lot of people found me through 3 Blue 1 Brown, which is cool. I appreciated the shout out from him a few years back. But yeah, as far as the course is concerned, I was actually surprised that there were quite a few people in the course who were specifically saying that my lectures were the ones that they appreciated. And now, look, I realize they probably said that for everyone, right? They probably said that for Alan, and they probably said that for David as well, and obviously Grant, because he's such a big name. But I think David and Alan were known in the Julia community beforehand, so obviously people were very fond and happy when they made content. And, obviously everyone was happy when Grant made content, but I have a much smaller following than Grant, and I don't have the I guess, impact in the Julia community as David and Alan did, so I was pretty happy that people were happy with the content I made. I don't know. I don't know what else to say. I very much enjoyed, maybe not so much making the videos, but I enjoyed the product, and I think the product is something that will stand. And so if you guys are interested in doing computational thinking courses, please feel free to check out the course next semester. Now, Perkinjay, I was expecting to find you oil painting. How, though? I've never done oil painting on the channel. I've never even talked about oil painting on the channel, except for that one time I might have talked about my favorite artist who happens to be an oil painter. So now I'm a bit confused. Did I do something to make people think that I was an oil painter? If so, I don't know the first thing about oil painting. I do apologize for that. I guess, it pains me to say this, but if you're here for, high quality oil painting content, please feel free to unfollow. You're writing a novel the other day? Oh, fair enough. Yeah, I do that a lot in my free time. So as far as writing Wednesdays are concerned, I do have a lot of content for an upcoming Writing Wednesday if I wanted to do one this Wednesday. But because I'm going to start doing a lot more time or a lot longer streams in the near future, I think what I'm actually going to do is intersperse the writing into streams in a different way. I haven't quite figured out how to do that. I do know for a fact that I do not want to do a stream where I'm doing a lot of heavy writing on stream. But on the other hand, I do want to include writing in stream. So I'm going to do some reading and stuff like that. I haven't really figured out the best way to do it. How does 2D ray tracer work? Wouldn't the camera end up being on a line? Yeah, so a 2D ray tracer, for the purposes of the visualizations that we were making, is not the same as a 3D ray tracer. So for example, let's do journal, a new page before, just to talk about this. If we drew a circle, let's say something like this, and we'll call this circle a lens, what the 2D ray tracer will do is it will literally just take the lines that are coming in, and let me see, just draw a line. Take a line coming in here, moving over here, and then coming back over here. And then obviously the same thing happens here where it goes in, over, and then out or something. So what the 2D ray tracer does, instead of doing the bit where you put a screen, I guess you put a screen, you put a screen over here, and you have all the pixels hit the screen. What you do is you just output the rays themselves, and so you can plot it in a traditional plotter or something like that. So you just kind of do the simulation, but just in 2D, and you just output them as lines on a plotting in any type of plotting software. Now, obviously, this is not what people would traditionally call ray tracing, because when you think about ray tracing, you typically think about not visualizing the rays, like what Danny Fritz is saying. Or rather, when you think about traditional ray tracing, you don't usually visualize the rays. Usually you visualize the color information that the rays receive. So it's a bit different. It was actually different enough that when I was making the video, I did actually tweet a bit and ask if people would consider a 2D ray tracer to be a ray tracer. And most people said yes. So I was like, okay, let's just go with it. But actually, I was really happy with that narrative. I liked the narrative of doing a 2D ray tracer, explaining how all the rays moved, talking a little bit about time stepping, and then moving on to the event-based model. I really thought that was a solid way to teach that lecture. Admittedly, it could have been done better, I'm sure. But I thought it went relatively well. I was pretty happy with that. Okay, so let's go ahead and start talking about the gory details of today's stream. Let me just Control Z a bit, actually. I don't need this extra page. Perfect. Okay, today we're really going to hone in on the number theoretic transform. So let's start talking about that. So the topics for today's stream, it's going to be really interesting. I'm actually, there's a lot we have to learn today, and I'm pretty excited for it. So the first thing we need to talk about is, oh, that's not a point. Try that again. Is the first thing we need to talk about is the Dft Matrix. In particular, we need to talk about how it relates to something known as a Fourier operator. So that's going to be the first bit. Operator. Then we want to talk about kind of an integer version. So int version of this guy up here. So I guess I'm going to do, because we do know that with the number theoretic transform, we can create a very similar form of the discrete Fourier transform. So what I want to do is kind of do an integer form of the discrete Fourier transform, and this is called a number theoretic transform. And so that's going to be the next bit. And then 3, we might have to do this on not Tuesday, but Wednesday. I want to talk about how to turn this into an Ffts method. So probably Cooley Tukey with number theoretic transform. So Cooley Tukey with NTT. So that's kind of the goal where we're getting by the end of this week. And so we're just going to start talking about it one bit at a time. I have a problem about improving myself in programming. I took some courses, I know the basics and stuff, I can work with classes, I made my own YouTube downloader even, but when I want to do something, I rely heavily on example codes, and if I can't find an example that suits the project in mind, I just get stuck and give up. What would you suggest me to do? Let's see. So Perkinji says you can solve that doing code exercises like in HackerRank. I document my code. Oh, Gibbous, that was super quick. It usually takes me hours to document my code. Right. So okay. So this is actually something that I do want to ramble just a little bit about. So maybe, welcome to another episode of Ramble Leos. But the point is, I would really like to hone in on this, because what you're talking about right now is the inability for you to creatively express yourself in code. And I will say that is something that most beginner programmers struggle with. And like Perkinji said, one way to do that is to solve example exercises. But really and truly, when you think about programming, at least in my mind, I really think about programming as a creative writing exercise. By that I mean, you have some sort of narrative that you're trying to kind of string together in your code, right? You know where you start. You know what your characters are. Your characters are like your classes or your structs. You know where you want to go. You know the story that the code wants to tell. And so now it's just a matter of getting all of these structs to talk to each other, and really finish the code all together, right? So it all has to form a cohesive narrative. And when you stop thinking about it as at least for me, when I stopped thinking about it as a thing that you have to engineer and started thinking about it as more of an art exhibition, or writing, or something like that, it became a lot clearer how to do that creative expression bit. So I'm gonna get off my soapbox now. That's all I wanted to say. But I do genuinely feel like that ability to creatively express yourself in code is the step that most people only learn by doing. And it's something that you just got to hop into and try. By documenting my code, I meant I documented a single prototype class. Oh, cool. Well, that's progress, Cool. So anyway, that's all I wanted to say. Let's go ahead and hop into the discrete Fourier transform matrix, and we'll go from there. So Dft Matrix, and let's see. Here we are. Okay. So what I'm going to do is I'm actually just going to read through this. Again, we'll see where we get. What I would suggest is trying to solve simple problems and implement simple algorithms from scratch. You already know how to implement steps in code, but the skill you lack is the ability to deconstruct a problem into a series of steps in the first place. Well, at least for me, I never, that wasn't my issue, but also, everyone learns differently, right? So, what I just said about creatively expressing yourself in code, that was my issue, but that's not everyone's issue, right? So everyone kind of learns in a different way, but by solving problems, you'll figure that out. Okay, so we're going to talk a bit about the Dft Matrix. I already talked about what a Fourier transform is, why you're interested in it, all this kind of stuff. So now let's hop into what the Dft Matrix is. Also, for those of you guys who are wondering why I have the title as How to Multiply, is because this is all related to some of the code that we wrote yesterday called the Shonhage Strassen algorithm, which is a way to do multiplication through Ffts, in particular through a convolution. So that's kind of where we're building up to. We're going to talk about DFTs, number theoretic transforms, the Cooley-Tukey method in integers, move into convolutions, and then finally back into the Shonhage Strassen algorithm. What things will you do in order to say count the number of time x appears in a string? Okay, so we're just going to kind of hop through this. And again, guys, if you have any questions, comments, concerns, anything like that, feel free to let me know, and I'll address it as soon as I see it in chat. Yeah, this is exactly what we need to go through. Cool. Okay, so in applied mathematics, a Dft matrix is an expression of a discrete Fourier transform as a transformation matrix, which can be applied to a signal through matrix multiplication. Fair enough. An endpoint DFT expressed as the multiplication x is equal to wx, where x is the original input, w is the n by n squared DFT matrix, and x is the DFT of the signal. Okay, I didn't do a good job explaining that, but you guys can see on screen what I'm trying to say. The transformation matrix W can be defined as W is equal to omega jk over square root of n. So the reason I'm talking about, I'm actually reading through this, is because this matrix is essentially the only real part of the DFT, right? So the idea is, in order to go from real space to frequency space, or the time domain to frequency space, what you need to do is you need to basically take your signal and multiply it by this Dft matrix, which is this matrix in here. And so the question is, what are these little omegas here? What are these, what are called twiddle factors? Cooley Tukey is a fun thing to say. The problem was, omega, JK, omega. But what I was going to say is, when we initially put the Cooley-Tukey method into the algorithm archive, someone helped with kind of refactoring the code a bit and changed it to the Cooley-Turkey method because he didn't realize that it was Cooley-Tukey, not Cooley-Turkey. It was kind of funny. Also, the Cooley-Tukey algorithm is remarkably interesting in its original development. So Cooley-Tukey, Cooley and Tukey, the developers of the Cooley-Tukey method, essentially, created what is the most common implementation of the fast Fourier transform people use today. Now, there are other methods like the Bluestein algorithm and stuff like that people use for Fourier transforms, but the Fft method, when you think of Fft methods, you almost always think Cooley-Tukey. That's just generally what people think. However, what most people don't know is that the method that Cooley-Tukey invented was actually created by Gauss like 200 years before. I mean, the same Gauss that made like everything else that you know Gauss for, like, Gaussian elimination, Gauss's Easter algorithm, I don't know, Gauss's law. The same Gauss also invented the Cooley-Tukey method before Cooley and Tukey did. And it's really interesting because at the time, that was just how he was thinking about implementing, how he was thinking about Fourier transforms. And it's really, I think, kind of interesting to see someone who's just trying to figure out what Fourier transforms were and decomposes it into such a way that could later be implemented in code and later would turn into what some people have claimed to be the most important algorithm of all time. Thank you for the suggestion of thinking creatively, investing time myself, and solving hackering problems where I can start with. Yeah, definitely do that. A lot of people in the community also go through and they do a lot of programming challenges and stuff like that. One big one that people are doing right now is the Advent of Code. Although you are starting late with that one, it's basically a single coding challenge every day in the month of December. Rather, that's not correct. One programming challenge every day in Advent. And Advent is, roughly speaking, the first 25 days of December, just before Christmas. So Carl Friedrich Gauss, yeah, that guy. Obviously that guy. I mean, what other Gauss is there? Actually, now that you mention it, Advent of Code is tough. Yeah, that is correct. But now that you mention it about Carl Friedrich Gauss, could be that they're like, what if Gauss's family just ended up being like really, really good? Like it's just a line of Gausses, and the Gaussian distribution of Gausses means that like Friedrich Gauss was the one that ended up doing the most math. But there were like Gausses around him that did a little bit of math, I don't know what I'm trying to say. My point is like, that like, at some point, if you just said Gauss's law, I think it's Carl Friedrich Gauss, but it could have been like his son or his father or something like that, or like someone else, or like someone along the Gauss line. And I would have just guessed it was Friedrich Gauss because he was like the peak of the distribution of Gausses, but probably it's all the same guy. Okay, that was a weird ramble. Let's keep going. Okay. So what are these omegas here? So these are primitive nth roots of unity. And yeah, so the way these work is that essentially they are like points on the unit sphere where the x-axis is the real axis and the y-axis is the imaginary axis. So all of these guys would be like omegas or something like that. And the idea is every time we, every line in this multiplication table, this array that we have here is essentially another point on that unit sphere is the way you can think of it. It's a family business. One of his 6 children must have been decent at math. And the fall off of the ability over time is Gaussian elimination. Oh no, that was not what I was thinking, but also like that has a bit of a sinister undertone when you think about it. Oh man, now I'm thinking about writing a mathematical thriller called Gaussian Elimination. Where Gauss is like a killer and he's just eliminating all of his enemies or something. Oh, that would be awful. That's the worst fanfic I've ever heard of in my life. I kind of want to make it and like read it aloud as like an April Fool's Day joke. I'm actually gonna write that one down. 1 second. I would have to make the video like really low quality as well. Anyway, 1 second. I think it'd be better as a horror story. Okay, so if you guys see a video coming up on April 1st, 2021, you guys know exactly what that video is going to be. Just forget about it until then. CyberGauss 277. Actually, so I was never really into the Cyberpunk series. I think Cyberpunk 277, but I heard that the game did not go over well. Even though it was super hyped, like everyone was really, really into it before it came out. Then after it came out, like I've heard nothing about it except that it's glitchy. Is that, does anyone here play Cyberpunk? Is that, how do I put this? Yeah, I just don't know anything about it. That reminded me of a website named after a mathematician that was full of programming challenges, but I forgot what it was called. So many bugs, buggy as heck. I watched it, didn't play it. Yeah, so was it, I don't know. Is a hot bun on Twitch? What is a hot bun? I assume it's like very popular. Outside of the bugs, I hear the game is excellent though. Oh, okay, well, I'm glad to hear that. I just heard it was really, the only thing I've heard of it are bad things, Oh, Project Euler, definitely Project Euler. That must be what you're thinking of. Okay, so where omega of e to the 2 pi I over n is a primitive root of unity in which I squared is equal to -1, we can avoid writing large exponents for omega using the fact that for any exponent x, we have the identity omega x is omega x mod n. This is a Vandermonde matrix for roots of unity. So what is this? In linear algebra, Vandermonde matrix, named after Alexandra Theophile, someone who likes theos. Vandermonde is a matrix with the terms of geometric progression in each row, i.e. an m by n matrix. Okay. It's literally just 1 alpha, alpha squared, alpha cubed, alpha n minus 1. Sure, fair enough. And then the base goes along the rows, and then the power goes along the columns. I'd recommend Project Euler too. Worse than the first release of NMS. What is NMS? Nuclear magnetic science, non-manageable NMS. What would No Man's Sky? Oh, okay. Project Euler is very mathy though, less CS specific. However, if you're into math, I hear Project Euler is quite good. No Man's Sky, yeah. Also, that one I heard was quite. No, I don't remember what was the problem with No Man's Sky at launch. People didn't like it, and I don't remember why. I don't really play too many games, so I don't really know myself. Oh, but I did think about something recently. So I don't play very many games, but I watch people play Guild Wars 2 a lot. I mean, not a lot. There's just one guy I watch in particular. And I was thinking about a collaboration with the guy, and I was wondering, they have like a full 3D render of all of the maps available, like online for all of the maps available in Guild Wars 2. And I was like, why don't we do like a clipping method? Like to try to find like all the places that you could clip out of a map. I think that'd be kind of interesting. The problem with No Man's Sky is that it was bad and shallow and did not live up to the hype. Too empty, repetitive, boring, and also with some bugs. Cyberpunk 2077 is just bugs and performance issues, plaguing an otherwise great game. I think plaguing, the second one is correct. Tons of bugs and basically missing content. Oh, for No Man's Sky. Yeah, so okay, hear me out. I feel like some people I feel like some people kind of jump on the bandwagon for some of these things. Like, I don't know. I feel like probably Cyberpunk 2077 is not as bad as people say it is. It's just that people say it's bad. And so everyone else is saying it's bad, you know? Like, there's like a bit of a hive mind there. And I kind of feel like it plagues internet culture a little bit. Oh, man, Gibbous is making me say plague as a verb. But it's okay. It can be used as a verb. Okay. So yeah. Okay, let's see, what do we have here? I'm actually kind of interested in the Vandermonde matrix here. So this is called Vandermonde Matrix. It is non-zero if and only if alpha I are distinct. The Vandermonde determinant was sometimes called the discriminant. Although presently the discriminant of polynomial is square of the Vandermonde determinant of the roots of the polynomial. Ah, okay. I should know this stuff. Starship, Starship, Internet Historia has, oh my gosh, I can't read, I'm so sorry. Internet Historian has a good video about No Man's Sky. Starship it's an amazing piece of technology and it's crushed. Starship, is that a game? For Cyberpunk to be compared with No Man's Sky, they'd have to release something that's basically Saint Row game or Arkham Knight. Okay, I don't know what either of those are, but they didn't. All the glitches are data to improve what they're with. Why can't I read today? All the glitches are data to improve what was a very big project. They released accessible, cool-looking New Vegas with spells. Is that what Cyberpunk is? So New Vegas is what is it called? New Vegas is like GTA, right? Like Grand Theft Auto. New Vegas, is that what it is? So okay, so Cyberpunk probably has like bullets and I don't know. I'm gonna. Oh, Fallout. I should stop talking at this point. I'm sorry. I swear, I really did think that New Vegas was a Grand Theft Auto game. I'm so sorry. I mean, sometimes I troll chat, but that was not me trolling chat at all. I literally did not know. But that's okay. Redo. Thank you so much for following. Really appreciate it. Okay, so let's just keep talking about math. New Vegas doesn't even have drivable vehicles. So here is, okay, fair enough. I didn't know that Grand Theft Auto was a game about shooting people for the longest time. Because the only time I played it was like once or twice when I went to a friend's house, and I thought it was a driving simulator. So like you do what you normally do, you know, you hang out in traffic, you drive around, and that's what I did. That's how I played the game. I had no idea there was a storyline associated with it or anything like that. I just kind of drove around town, and for some reason the cops were always after you. So I didn't really understand that part. But anyway. Okay, so we have this Dft matrix. Let's go back to the math here. We have this Dft matrix that we're looking at here. We know it's a Vandermonde matrix. I am a bit... Okay, I think I'm just going to read through this and we're just going to knock it out. Fallout New Vegas does have a bunch of bugs and performance issues and general jank, but it's also an excellent game, and that saves it. Fair enough. Like Midtown Madness, I don't know what that is. Well, the main focus is driving around. Is it? Cool. Cyberpunk 2077 is much the same to my view, except the bugs are currently too big to deal with. Well, yeah, okay. It's kind of like, there was one game I was really interested in playing. It was called A Hat in Time. Hat in Time. Yeah, this one. Yeah, I really wanted to play this game, and it came up for the Switch. But it was just really buggy, and I couldn't play it. Let's see. Hey, Trash Hawk, how are you? To be fair, it's called Grand Theft Auto. Kappa? Oh, okay, yeah. I don't know what you're copying, but if it's called Grand Theft Auto, you're right. It has to deal with cars, right? I'm gonna buy and play the game in like a year or two once they've patched it all up and it's smooth. Hat in Time is great, I've heard. Yeah, it looks pretty good. I mean, like, I don't know. Maybe I'm just a fan of those types of videos. 1.5 root. Oh, I see. It's a picture. I might just be a fan of that type of content because that's the type of content I used to play. You know, like Spyro. Spyro. I actually don't... I can't think of any other games that I played. Like, I used to play Spyro, Digimon World, and Guild Wars. These were, like, the only games I played. And really, I mean, obviously, Spyro wasn't a game that you could play that long. Neither was Digimon World, but I played Digimon World a bit too much. Yeah, actually, okay. I probably played Digimon World about as much as I've played Guild Wars. And I played Guild Wars for, like, 3,000 hours. So I think that's, like, where all my childhood went. It's an old game, probably in the 90s or early 2000s. Only driving around a city, sometimes racing with bots. Ah, interesting. Cyberpunk is going to pull a No Man's Sky, probably. Right, that's what everyone's been saying. Again, it's one of those things that I didn't realize. So No Man's Sky now people like, I assume. Actually, let me just go to Twitch really quick. Twitch over here. Let me just see if I browse Twitch. What is the most played game? The most played game, Minecraft. Oh, Cyberpunk is one of the most played games. Like, clearly. It's popular, right? For multiplication, yeah, so what we're doing right now is we're looking at what's known as the oh, hello there, 1 second. We are looking at something known as the Shonhage-Strassen algorithm. So the idea here is that we have, we actually already implemented this yesterday, but I'm just going to make it bigger to kind of explain what we're doing here. You take two numbers, and the way you do the multiplication is via a convolution, and the way you do the convolution is with the Fourier transform. So what you do is you take the two numbers, you Fourier transform it into whatever space you're Fourier transforming it into. You do the multiplication, then you Fourier transform back, invoking the convolutional theorem, and thereby doing the multiplication. There's a lot of bits here that are very confusing. Like, for example, the first thing that confused me was that multiplication was a convolution. Once you kind of wrap your head around that, you can then start to understand how you can use the convolutional theorem for this. So right now, today, we're actually really inspecting the Fft bit, and we're going to try to create a discrete Fourier transform matrix that is purely in integer space, because this Fft works purely over integers. And though we did do the, what is it called? Complex Fourier transform before, and it works for multiplication. I'm very interested in this number theoretic transform and seeing if this will help us gain a little bit of intuition for Fourier transforms themselves, so I can kind of repurpose the chapter that I already have on FFTs in the algorithm archive. That's where we're at. I'm sorry that was a bit long. I'm doing kind of a really rambly job of explaining things today. Let's see. Not that I'm playing it, not really a AAA kind of guy. Yeah, I found that I also don't really like AAA types of games, you know? It annoys me a bit when people make that comparison, because to the best of my knowledge, No Man's Sky was unplayable and bad at launch and eventually became good, but Cyberpunk is unplayable and good right now. All people need to do is all it needs to do is become playable. Yeah, that's also fair. I don't know, like, this is stuff that I don't really know about, but I do know that, like, I mean, I guess I played Guild Wars. Is that a AAA title? What is a AAA title? Why am I rambling about this? What is a AAA title? AAA title. Okay, a AAA title, sure, is an informal classification for video games produced and distributed by mid-sized or major publishers, typically having higher development and market budgets, okay? In the mid-2010s, the term AAA Plus began to be used to describe AAA games that generated additional revenue over small time in a similar fashion to MMOs. So, okay, so hear me out. Is Guild Wars? Guild Wars must be a AAA game, because ArenaNet, the company that makes it, okay, but ArenaNet didn't exist at the time when it was made. So really, Cyberpunk is going to pull a Car Mechanic Simulator 2018, a reference nobody understands but me. Fair enough. They're usually pretty demanding on resources as well. Yes, right. I was trying to say that it will probably get better. Probably. Yep, it's AAA. Okay. I'm not talking Guild Wars 2. I'm talking about Guild Wars 1. So before the company before the company had any money. I guess probably. Yeah, must be, because NC Soft owns it. Anyway, let's just keep going, talking a little bit more about math, because at this point I'm talking about stuff I have no idea about. Oh, but I was thinking, okay, like, I have been considering, Wichita, thank you so much for following, really appreciate it. I've been considering, doing a playthrough of Guild Wars again, where I just play through it without using any spells or something like this. Like, just doing, like, a Guild Wars challenge. But then I realized, like, there's nowhere to publish it, and I'm not really interested enough in it. Guild Wars 1, released in 2005, predates this AAA concept. Wasn't it released before that? Guild Wars, I thought it was 2002. But I could be wrong. I'm wrong about a lot of things. It was 2005. Oh, wow. I didn't realize it was only 15 years old. I thought it was older than that. Cool. Okay. So let's get going here. So we have this large matrix W. I realize it's a bit of a shock going from, sounds like a waste of time, no spell run. Okay, maybe. It's one of those things, right? Who's going to watch that? You're right. Okay, fair enough. That was kind of harsh. Okay, right, like, a lot of people watch these types of challenges for, like, games like Pokemon and stuff like that. So I figured, you know, probably it would be worth watching for other games that are, like, in my mind, better than Pokemon, which would be, like, Guild Wars. But also, like, people don't in general, think about that. And also, I realize that my community is very much not a gaming community. And so because of that, people in my community probably would not be too interested in that. The modern understanding of AAA really starts around Far Cry in 3. Far Cry. No, I was thinking Crysis. Would have to stream it. Yeah, I would have to stream it. Like that's what I would do. I'd stream like a no spell run for Guild Wars. I mean, again, the question that Onidu said. I'm sorry, I'm really bad at pronouncing names. It's a question, right? Like, if I were to do gaming on stream, I can guarantee you I would not have an audience for gaming on stream. It's just not something that people like watching from me. And that's totally fair because I actually don't really like playing games too much. The exception is Guild Wars, which I get bored of relatively quickly. And Digimon World, which I still play. Not Digimon World. Anything after Digimon World 3, I don't play. But every now and again, I will play Digimon World again. This type of stuff, you know? For the audience, Subnautica probably is the best game to be watched. What is Subnautica? I'm not interested in playing games I haven't played before. I'm really sorry about that. It's just, I don't have the time or patience to learn a new game or a new, like, way to play a game, you know? Like, I could play Smash Brothers. I'm pretty good with Wii Fit Trainer on Smash Brothers. I was in, like, the top 5% of players at some point, but only with Wii Fit Trainer. I could play no other character. For the audience, Subnautica is probably one of the best games to be watched. You could probably play TIS 100 and get away with it. Crysis and CryEngine and Crytek. Okay, yep, time for math. Let's go back to it. I'm sorry, I've been rambling for a bit. It's a ramble day. Math. It's underwater survival game with some sandbox elements. The only other thing I've thought about doing is doing like a mod pack for Just... Huh? No, not Just Starve. Don't Starve. Because those are kind of fun. Okay. So let's get back to math because, you know, Oniru is right. I have not been doing any math. And yeah, people are obviously people are clamoring to do more math on stream. Like this is this is actually pretty good. Okay, so we have this Dft matrix that we've been staring at for the past 20 minutes while I've been rambling about other things. I'm going to read through this next section and we're just going to try to figure this out. So we know that if I go here to, where is the... actually, let me go to the Shonhage Strassen algorithm. And then we're going to, let's go here, go down a bit, and there should be a fast Fourier transform, discrete Fourier transform here. No. What am I looking for? Convolutional theorem, linear convolution, negacyclic convolutions, maybe not what I'm looking for. Primitive root of unity, number theoretic transform. This link right here. Perfect. And this brings us to another matrix that we have that I wanted to try to figure out today, which is a number theoretic transform. Now, if you note, the matrix is kind of the same. You've got ones and ones. And if we look at the Dft matrix, we've got ones and ones. But then here is where things change. We have omega, omega 2, omega 3, omega squared, omega cubed, omega squared, omega cubed, so on and so forth. And here it's different. Like clearly this is a bit different. So what I wanted to be able to do today was create this number theoretic matrix and just kind of mess around with it a bit. Because we already have the ability to do DFTs. And so now I kind of want to explore it a bit more. So let's kind of hop into that. Just Starve is when you mod just cause to add a hunger mechanic, but forget to implement food. I don't know what Just Cause is. I've never heard of that game, but Just Starve. Oh, Just Starve. I was thinking Don't Starve. Okay, so let's keep going. And I think that's what we're going to do. We're just going to hop into it and just try it. Because at this point, yeah, we have the matrices available. We have kind of a rough idea of what the matrices are. And so I'm just going to kind of create the DFT matrix and, I don't know, like plot it out, see what's going on. And then we're going to try to create the number theoretic matrix and plot that out and see what's going on and go from there. Your viewership has doubled while it's rambling. If there's one thing I do good, I do good? Oh my gosh. I apparently don't do good English, but if there's one thing I do well, it's ramble. So let's keep going. CD Projekt, Simuleos, and I think I have FFT in here. L is here. VIFFT. Oh no, where is it? FFT slow probably, .jl. DFT, what do we have for DFT? So here we have DFT slow. Do I have the DFT matrix? No. L is here, CD back directory. Where did I put it? Would there be a Dft Matrix? Pretty sure I would have put it in FFT. Okay, what do we have here? Dft out.jl is probably where I put it. So let's go over here. CD project Simuleos, CD FFT, and let's just mess around with it. About info. So today we are working on a multiplication algorithm that requires doing fast Fourier transforms. These fast Fourier transforms are obviously built from discrete Fourier transform matrices. So today we're trying to figure out how these matrices work and why they work that way. So what are these matrices? Let's go ahead and do mirage check.png. Okay, so this is a discrete Fourier transform matrix. That's what it actually is. This is the real part, and then we have the imaginary part as well. So yeah, I'm gonna just try to mess around with this and see what we can figure out. That's what we're doing today. If we go to the matrix in here, I think people do plot it. Here, this matrix in here. So these are the matrices that we're messing around with today. And yeah, so in principle, it should be that if I plot out the rows of this matrix, we should be able to see a straight line, like a single sinusoidal oscillation, a double sinusoidal oscillation, stuff like that. Is Wolfram Alpha for mathematical calculation? Thanks, man. Appreciate that. Okay, so we're gonna go ahead and clear here, and let's do ls, and now we're gonna just do Julia. And what do we have? Let's go into vi dft. It's been a while. I mean, some of you guys might even remember this code. Okay, so what is this doing? We are creating Fourier Operator, and we're creating the discrete Fourier transform. We're only interested in the discrete Fourier transform, so let's go ahead and have this function actually return back something else. So we're gonna have it return back the matrix A. Wonderful. Okay, so we're gonna include, I think it's dft out.jl. Yep, perfect. Run that. It has to precompile images, so let's just give it some time. I calculated the gravitational force between two hydrogen atoms on the opposite ends of the universe, observable universe. That must be really, really small. Because two hydrogen atoms, so it falls off as 1 over r squared. It falls off as 1 over r squared. So that force is super small. Speaking of force integration, if you guys are interested in doing large galaxy simulations, let me know, because that's something that I'm considering doing. 10 to the minus 118 scale. Yeah, that's probably about right. But yeah, so I've been thinking about doing the Barnes-Hut algorithm again. That if you guys, no one's gonna remember this. 2 years ago, we tried to do the Barnes-Hut simulation, which is a simulation for n-body simulations of galaxies and stuff like that. I wasn't able to do it because my 3D visualizer at the time was Blender, and Blender could not do these types of visualizations. So yeah, we ended up like trying to do some sort of, what was it? We ended up trying to do some sort of OpenGL code to get this all to work, and that didn't work out. But I'm thinking about giving it another shot to do some really cool galaxy visualizations and stuff like that. Okay, so I'm going to say dft is going to be equal to dft out, and we have to read in n, which is the int64, and then the output file string. So we're just going to say 1024, and then out is going to be called check.png. Sure, that'll do. Okay, so now we're going to have our 1024 matrix, and we can kind of mess around with it. Okay, so let's go here, quit, and let me just take a look at check.png. So mirage check.png, and this should be a 1024 by 1024 matrix. Looks like it is. And here's our DFT matrix, guys. I think. No. Is it? The DFT matrix should have a real and imaginary part. This looks to me like it's only one component of the DFT matrix. Let's take a look at what we have here. Yeah. Oh. I'm dumb. I'm so stupid. It obviously is both a real and imaginary. It's both. What we want to do is output the transform matrix. Okay, the real part is red, the imaginary part is blue. This is before we did domain coloring, so I wanted to do a very simple way to plot imaginary and real components. So that's what I did. Okay, so now we have the DFT matrix. DFT, oh, I forgot to include it again. Now we do DFT. Okay, and this should be the appropriate... Oh, why is it RGB again? Did I forget to write? Okay, try it one more time. Oh, Dft is equal to... Yeah, Dft out. Okay, so now we have our imaginary complex components. I'm just going to try plotting it, see what we have. Let's see. But will it be... What am I doing with my life? 1 second. But will it be very... that'd be really cool, but will it be very resource intensive? Oh, it will be. I'll explain that in just a second. What is the input for a galaxy visualization? Is there a database of known of the location of known stars? Man, you a computer scientist? A bit. I wish WA had a consistent way to specify sub-expressions. What is WA? Adding too many natural language expressions, it trips up the AI magic, even with parens. Wolfram Alpha. Okay, I never would have guessed that. So we're going to go Barnes Hut. Okay, so this is when I say galaxy simulation, I'm not going to put in real parameters here. The point was to do a simulation that looks something like one of these, but in 3D. The idea, I really wanted to be able to do a visualization of a large 3D galaxy that spins around and all collides and everything until you see this kind of disk nature appear. It's been covered by both, I think, Physics Girl and also Minute Physics. They've all kind of talked about how, if you take these large 3D objects, they'll eventually form a 2D disk. But these things have not actually been like visualized properly in my mind. Well, they probably have. There probably are really good visualizations of it. But I want to do something that's like really crisp and clear and clean and all that kind of stuff. As far as the computational complexity, the way that this algorithm works is obviously you do a force integration like you normally would, but you also add on top of it something that's known as an octree or a quad tree. The idea here is that every single particle gets its own box that is composed of like children boxes that have parent boxes and parent boxes on top of that. So if you're a particle that's really, really, really far away from another particle, instead of looking at this huge group of particles as individual boxes, you're going to look at it as one single parent box. That way you don't have to do a force integration with all of the individual particles, but you can instead do the force integration with just one big clump. So that's kind of how you save on computational complexity, and that's why it's interesting. 909, thank you so much for following, really appreciate it. I've definitely seen that video by Minute Physics now that you mention it. Yeah, it came out a while ago, like, I don't know, maybe 10 years ago, a long time ago. Like, I have no idea, I have no scale of time. But what I will say is it's an interesting visualization. I think it could turn out really cool. I was actually thinking about doing a game that you could play, like the Barnes Hut game. I don't know what it would be called, but the idea is you're like a space explorer and you're kind of going through space and you play with this little twiddle factor to basically render more or fewer particles. And as you render fewer particles, you speed up, you go faster. But as you render more particles, you end up going slower. So you can kind of get your bearings. So you basically go really, really, really fast. And then, you try to find your way to some sort of goal somewhere. And as you're going super fast, you can kind of like leap around and use gravity in a different way. And so the idea was that like, there are two aspects at play here. One, it's kind of a speed run. You want to get from point A to point B as fast as possible. So obviously you want to see as few particles as possible. But two, your gravity is actually influenced by the number of particles on screen. So what you want to do is you want to make it so as you're going nearer other objects, you want to see some objects. And so you're kind of playing this little factor to try to move your way through this 3D space and see, certain particles and not see other particles. I don't know. It's kind of an interesting... I thought it'd be an interesting way to give people intuition that the computational speed is, related to the number of particles on screen, and also kind of have a cool little mini game to go with it. It's beautiful. Let's see. I've definitely seen that video. How to calculate the time my processor will take to calculate a mathematical equation. I'm not really sure. I think you just have to, kind of do some benchmarks. Does that need gas-dust simulation, or is it just gravity interaction of particles? It's literally just an ND, or rather an N-body particle simulation. That's all it is. Now, there are ways you could do like kind of more of a dust or a volumetric approach to this, and I think there are actually. Oh, in fact. Okay, so hear me out. Okay, just I have something else I need to write down because I'd forgotten about this, but I'm really excited about it, and I'm happy that you reminded me. Oh no, I just dropped papers on the floor. Oh, I'm the worst type of person. Give me a second. Okay, so there was this time, long time ago, and in a country far, far away, where I did superfluid simulations, and there was a paper I wanted to publish on vortex detection. Right. Okay. So the thing is, this idea of the Oct tree only really works when you're splitting up space. Oh gosh, there were so many cool ideas here as well. Oct tree for Fft. 1 second. Okay, so here's the idea. Oh, I just hit the microphone. Oh gosh, I don't know why I'm rambling about this as well. But let me know if you're interested in this, because this is something I was thinking about slotting into some of the videos that I'm making. I'm trying to find videos of things that are also equally publishable. So I'm just going to draw a box here, and inside of the box I'm going to draw a circle. This circle on the inside is your superfluid. So super. And on the inside of this, we're going to have a single vortex. And this vortex is going to have a 2 pi complex phase winding. That is to say, the complex phase goes from 0 to 2 pi around it, right? Now, in order to properly identify vortices, oh, no. Oh, it gets even better than that. In order to properly identify vortices, you basically have to go through the entire simulation and find these 2 pi phase windings, right? So I was thinking of a way to do the simulation on an Oct tree grid, such that the grid itself is like small in places where you need a lot of density, i.e. around the points over here where there's like a high gradient, and around the vortices, but not out here or in the middle of the simulation here. And so there are a whole bunch of really cool things that I was thinking about doing here. So vortex detection Oct tree for pseudo-spectral method. I'm just writing these down. So Oct tree for pseudo-spectral method. Yeah, so the nice thing about, so what we used to use was a pseudo-spectral split operator method to do our simulations, which meant that you basically did a convolution every step. You did an FFT forward, multiply FFT back. Now, the question of why split op is a convolution, that's actually something I'm a bit interested in that I should probably also talk about. So split op convolution. But because you split, because the Oct tree is kind of split evenly divided, like in the middle, so you have like like 2 big boxes and then smaller boxes and smaller boxes, and that's kind of the way you do a recursive Cooley-Tukey approach anyway. I thought it'd be really interesting to do a pseudo-spectral method, that is to say a PDE solver on an Oct tree based grid. Yeah, is anyone interested in that? Because I'm actually very interested in this. So the idea of just doing a simulation of a partial differential equation, people do that all the time. It's not particularly interesting, but doing it on a really weird mesh thing is kind of interesting, and I'm very interested to see if this is something that other people are interested in. Stars, or rather pseudo-particle stars, i.e. 1 particle, or it's like 10 to the 4 stars. What kind of particle? Yeah, that's exactly what it is. It's some sort of star, or maybe a planet or something. It doesn't really matter. It's a particle. A particle is a particle, right? That depends on a number of parameters. Everything like what data will it need to load? Does it all fit in the cache? What is the speed of the processor? How expensive the instructions, etc. Like Simuleo said, it's best to just do a performance test if you really want to know the execution time. Yeah, that's totally correct. Nothing, in my opinion, nothing really beats a good benchmark. You can do all of these different you can do all these different benchmarks of similar hardware, but the truth is, even if you're running like almost the very same processor as someone else, chances are your processor will still run up to 10% differently, either faster or slower than someone else, just because of other variables that you really can't really count on, like maybe your thermal paste went dry and now all of a sudden your processor is hotter, or something like this. Maybe the cooling in your tower isn't as good, or something, it could be that you got the lower end of the i7 and the other person got the higher end of the i7. I don't know, like there's a number of different reasons why your hardware will run differently, and it's kind of hard to tell. Anyway, I wrote this down. Oh man, that'd be super cool. I'm gonna do it at some time. It's just the question of whether I do it this upcoming year or I do it later. Okay, so let's just kind of mess around a bit. that said you do get a feel for how expensive some things will be after you have some programming experience. That's true as well. And you know, I don't want to talk about the elephant in the room, but there is the elephant in the room that is big O notation. There is a way in which people will classify algorithms based on their overall asymptotic speed, like how fast they will be when how fast they will be as you scale up the problem. And this does give you a good grasp to understand, like, you know, if you run code and that code takes an hour to run, and then you double the size of the code base, or you double the size of the problem, you know, how will that scale? Like, it does give you a good understanding of that. The problem is so many people rely so heavily on this scaling parameter that they tend not to really focus on the finer details that are sometimes more important to the actual code base, right? So yeah, it's important to take into account how big O notation works, and the fact that, you know, as you know, the problem will scale as, you know, n log n or something like that. It's important to talk about this. But I think equally important is to show those benchmarks. You know, that's the problem. It's definitely important, but two n log n solutions don't necessarily take the same amount of time. Exactly, right? Can I crowdsource some unimportant problems? I mean, in some sense, I'm not saying that's what I'm doing, but in some sense, none of the problems I'm tackling are like particularly important. None of the problems I'm tackling are problems that, you know, like, will get a lot of citations. But what I like about the problems that I'm tackling is that they are problems that people can immediately grasp and understand. And I think that's cool. Like, what's the least important problem? Probably, what is the worst sorting algorithm would probably be one of the least important problems. Like, what is the worst X, Y, or Z? Imaginal is probably like the least important problems. But also, they're still fun, you know? Like, worst sort is the worst sorting algorithm. It has a summation and big O complexity for how bad it is. And yet, at the same time, it's super interesting. Like, remarkably interesting. I love it so much. It's also one of my least liked videos on YouTube. I think it's because I did it in 2016, and there was a meme that, you know, 2016 was the worst sort of year, and so I named the video 2016 the worst sort of year, and I talked about a whole bunch of bad sorting algorithms. So I think I'm going to change it, like change the video just to be a video about worst sort, instead of being 2016 the worst sort of year. In fact, I should do that, because too many people are getting pissed off because it's 2020, and they're like, 2020 is so much worse than 2016. But I don't know. Currently have salt going past its use by date. Wait, I don't think that's that. Okay, I see what you're saying. I wasn't even thinking about this class of problems. Okay, let me see using plots. And let's just plot something, just for fun. You know, who knows? Isn't worst sort one that doesn't need to sort the numbers? Oh yeah, that is correct. So the way worst sort works. Oh, it's beautiful. It's by far the most beautiful algorithm I've ever seen in my life. So you have a list of numbers. So let's say you have a list of numbers, and you know, it's not sorted. So you don't really know what the list of number is. So let's just say it's like 3, 1, 2. That's your list of numbers, right? Okay, so you, as a person having to sort this array, presumably, because you're using some sort of sorting algorithm, don't know the appropriate way to sort the array. So the question is, how do you do it? Okay, good question. Well, one way in which you could sort the array is by listing out every single permutation of the array. So for example, 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Okay, and you know that one of these permutations is going to be the sorted array. Okay, you just have to go through each one and ask, is that array sorted? Okay, but now you have the same situation, right? You just went through this set of numbers, and you were trying to figure out how to know if that's sorted. So now you have to go through this set of numbers and figure out, you know, in what order do you go through this set of numbers? You know, what's the best way to go through that? So what you do is you then permute this array, right? So what you've done is you permuted all the arrays to create, you know, you first had to sort through 3 elements. Now you have to sort through, is it 6? I feel like it should be 9, but maybe it is 6. So now you have to sort through 6 elements. I must have missed something. I feel like I missed some elements. But the point is, you take the array, you permute that, and then you ask, what order do you go through the list of permutations? Then you take that array and you permute that. And then you say, how do I go through this? And then you take that array and you permute that. And so the idea is you consistently just permute the array over and over and over again. It is 6. You're right. And that's what you do. You never actually sort the array. You just keep permuting it, trying to find the new list of arrays that you sort, right? And that's it. It's kind of funny. And then in the end, finally, when you're bored of using worst sort, you use like bubble sort or something. What am I doing with my life? Isn't worst sort the one? What if simulate the galaxy collision based on electromagnetism instead of gravity? Electromagnetism and gravity both work. So one is based on Coulomb's law, essentially. The other is based off of the other one's based off of basically Newton's law of gravity. I think it's Newton's law. Anyway, the point is they're both 1 over r squared. So you're going to create basically the same result whether you go through electromagnetism or gravity. That's coming through someone who used to do plasma research, and I did dusty plasma research where I actually did these simulations with electromagnetism. It is the same as gravity for the bulk of the simulations that you're going to look at. It neutralizes, so it's not infinite, even though the equations are similar. Don't know what you're getting at there, Maverick Twitch. Maybe, well, okay, it depends on how you do the simulation, I suppose. Here's my proposal, the worst sorting algorithm. I just don't think you can. Okay, there are other worst sorting algorithms out there, like miracle sort, where if you just continually check whether the array has been sorted, and then you hope by some miracle that it will be sorted eventually. So you just keep checking. Like the whole algorithm, the algorithm does nothing. All it does is consistently check that the array is sorted, and that's it. The unsorting algorithm, an unsorting algorithm is really easy though. Oh, but what would be interesting is taking a sorted array and turning it into the worst possible array to be sorted by different algorithms. Okay, so hear me out. Like for example, merge sort has certain properties, right? And so the idea would be you create an algorithm to create an array that would take the longest time to be sorted by merge sort. So Martin says if instead of gravity simulation, we do it using EM. Correct. And I say that that's the same as gravity because they're both 1 over r squared. Discard the list to determine the host system type and choose the appropriate method. 3, exploit security hardware bug and destroy the host system on a physical level. What? According to me, positive and negative charges cancel each other, but mass doesn't. That is correct. Okay. So what you're saying, okay, I misunderstood what you were saying. I'm saying the following, just to make sure we're clear here. Obviously, positive and negative, we have a positive and a negative here, right? These guys will be attracted to each other with a force of basically 1 over r squared. There's some constant here. But 2 positives will be deflected from each other. They will be pushed away from each other with a force proportional to 1 over r squared. I was thinking that all of the charges in the system are positive, but you were thinking that we have a distribution of positive and negatives. I understand now. Because in the dusty plasma simulations, what end up happening is you have like a single positive particle, but this positive particle, it's not really a positive particle. We'll say it's a neutral particle. And this neutral particle will have basically be this giant sticky glob. And the idea is this giant sticky glob is going to be going through a plasma, and the plasma is completely filled with electrons. So what ends up happening is this giant sticky glob gets a whole bunch of electrons in it, like maybe 1,000 electrons on it. Right, 1,000. And then, another glob over here also has roughly 1,000 electrons on it. And so the idea is that these are both negatively charged, and then they act essentially as if they're repelling each other based off of gravity. So... but they would all still be attracted towards the center of the plasma, which might be here. Something like that. I just realized, I see what you're saying. Positive and negative with collision would be the same as gravity. I'm wrong. I'm sorry about that. Yeah, I actually am now realizing that I was a bit off when I said it before. Yeah, the only way you would have a gravity-like simulation. The only way you'd have a gravity-like simulation would be if if every particle was attracted. So it's the opposite of the electromagnetic particle, but then you're just gonna have constant acceleration away from each other unless you have some sort of plasma or something pulling things back together. I guess that's an interesting question. If you had a plasma the size of the universe, what would the universe look like? Right? Like, what happens if you do a giant plasma simulation? I don't know. Anyway, that's a question for another day. I'm not so interested in studying that. Let's go back to the Dft matrix, which I have totally not talked about at all today, even though today's supposed to be all about the Dft matrix. All right, let's go. We never say how much the sun exerts an electric force on the Earth. That's my worst sorting algorithm. It doesn't sort a list. In fact, it destroys a list. You're programming all of the data on the computer, and in fact, the parts out of which the computer is made. Right. So that would obviously not work. What about a galaxy simulation where all the stars are black holes and you have relativistic effects? I think actually this would go into a bit of computational field theory, which is a field that is very underdeveloped, and I would love to see more people kind of jump into. Does that not load? Well, it's just some guy's random group, I guess, or girl, some person's random group. Yeah, I'd love to see more computational field theory. It cut off most of the number. According to me, positive and negative charges cancel. I see. I misunderstood. I apologize for being dumb. We never say how much the sun, let's see. Actually, no, the worst sorting algorithm does this, but first self-propagates itself across every computer on the entire internet and destroys every computer it reaches. It's probably true. Void sort system removal. Certainly less favorable than a sorting algorithm that simply hangs forever, like the plasma universe model, the photon universe model. The photon universe model would be a bit different. Also, now that I think about it, and just hear me out here, there was a... Okay, this is not related to the photon universe model at all. This is related to Gibbus's other comment when he said, oh no, Alexor's comment here, where system rm-r/. There is a Linux distribution that will just destroy your computer if you ever have a compilation error or something like that. I don't remember what it is, but I've always wanted to use it. I know what it does is just destroy your system if you have like an error of some sort. Like if you screw something up, all of a sudden your entire computer is wiped. And that's just what happens. And I've kind of wanted to use it for a bit. But oh well. Okay, so here's the transform matrix. We have the ability here. Let's just do plot of x. What is it? What do I call Dft of :1? And let's just do the real of that. Real of that. And we should get a straight line. Let's see what it looks like. If a command has a non-zero exit code. Yes, something like this, I think. Let's see. If a command, yes, reminds me of the one Mac game that deletes a random file for every enemy you shoot. Wait, really? Okay, let's do 2. Okay, good. Let's do 3, 4. This is exactly what I wanted to see. So essentially what we're seeing here is that the Dft matrix, which is this giant matrix that we just showed before, check.png, is essentially a list of all ones, and then you get a single oscillation, and then 2 oscillations, and 3 oscillations, and 4, and then 5, and 6, and so on and so forth. So that's what this Dft matrix is. It's just a set of oscillations. So the way you can think about this, and the way that I personally think about this, is that this first line is basically going to take whatever signal that you're reading in and select out anything that essentially doesn't have a frequency. The next one's going to select out anything that roughly matches a frequency of 2 pi. The next one will select out anything that roughly has a frequency of 4 pi, and then 6 pi, and then 8 pi, and so on and so forth. So that's kind of the idea. cd/ and get in it. Oh, I was thinking about watching you trying that on stream. With some other computer. We might do that. We did an Arch install speed run that I wanted to put on my YouTube channel, but I never did because I'm a noob. It sounds like a series of frequency correlations. Essentially, that's what it is. Let's see, Julian115, thank you so much for following. Really appreciate it. In fact, that is what it is. The way you can think about this is it's like some 8-element clock. So 1, 2, 3, 4, 5, 6, 7, 8 or so. And the idea is that, oh, how do we think about this? The idea is that you're kind of doing a sine and a cosine along this clock, right? So the equation for a circle is sine squared plus cosine squared equals 1, right? And that will give you the radius of 1. And so the idea here is you're kind of moving yourself around this kind of circle object. And as you're moving yourself around that circle object, the idea is that, you know, you go around 1 pi, or sorry, you go around 2 pi, you go around 4 pi, that's twice, you go around 1, 2, 3, 6 pi, and so on and so forth. So the idea is you're kind of like asking how many times you go around that circle, and then you're just discretizing that along the grid. So that's kind of how you create it. So it's like a series. So do GitHub repos have storage limits, or can you upload your entire OS? There used to be storage limits, but yeah, not anymore. Also, we haven't even started talking about FFTs. FFTs are another beast entirely. The way you speed up the matrix multiplication is by recursively subdividing the elements. It gets confusing, and I generally have questions as to, you know, I used to have a better understanding of it, but I did a poor job describing it on the algorithm archive. My point is, as you recursively subdivide that array, the question is, how and why are you able to recursively subdivide it in the way that you can, such that you actually get the same DFT calculation out? And that's where I'm a bit confused. So that's what I need to talk and learn about. What do we have here? Elixir, some have. What is this? Manto S? Go over here. What is this? Network Investigators Forensic Toolkit. Oh, okay, fair enough. Yeah, this is literally just an open source operating system. Fair enough. More notably, oh yeah, MS-DOS. Yeah, DOS. Okay, so here's the thing. Everyone said that DOS was open source, right? And like everyone made a big deal about this. But the truth was, like, I thought, and maybe I was wrong about this, I thought that people just kind of tore apart the code when it came online. Basically, I barely understand FT to begin with, let alone DFT and FFT. Yeah, so for me, for the record, the OS never actually stood for operating system. It stood for open source. But yeah, okay. Like most people, okay, so the name itself is like a really weird mishmash of a whole bunch of different things that you wrote an OS? I didn't though. So that's why I'm thinking about, changing the name just to be Laos, or maybe Laos Labs. In fact, I think Laos Labs is what I should probably change the name to, because I'm thinking about doing like research and stuff like that. I like the name Laos Labs. I think that's pretty cool. So I'm thinking about changing it to that instead of Laos OS. But I haven't really done it yet. So I might do that next year. But yeah, Laos OS was supposed to be like Laos operating system. Well, Laos open source. And I was supposed to talk about all the open source stuff. I didn't, because I just never did. So MS-DOS was just pure ASM. I mean, at the time, I'm sure. Yeah. I mean, also, like, it does say 100% assembly, which is kind of neat. Okay. So here's our big image again. Okay. And we have the ability to plot everything. So good. We know what that is. So what I'm going to do next is I'm just going to go in here and we're going to create a number theoretic transform out. So in here, we're going to do function NTT out, right? That'll do. And we're going to do n, which is going to be equal to int 64. I'm not even going to worry about outputting it to image. Okay. So we're going to say n is going to be equal to I for I is equal to 0 to n minus 1. Okay. And then we say k is going to be equal to n prime. And then here we're going to say the transform matrix is going to be equal to. Okay, so here's where we need to think about it. I just need to figure out how we're going to do the number theoretic transform exactly. So let's go there and let's see what this array actually is. Where are we? Discrete Fourier transform? Yeah, that's what I want. Okay, so it's going to be... I still don't know. I'm really confused here. Laos OS definitely sounds like a Linux distro. Right, yeah. What else would you make it out of? What else would... MS-DOS. Yeah, right. Are we forking MS-DOS? No, we weren't. I just was looking at it because Gibbous put it up. I wanted to write a kernel. Okay, so back in the day, I was super into open source stuff. Like really, like I'm still into open source stuff, obviously. But you know, back in the day, I was really into Linux. I loved it so much. I still do. But there was just something about it that I was really, really, really interested in. Like I spent hours doing nothing but compiling wine. That was it. That's how I spent my afternoons. That was party time for me. Like I genuinely enjoyed like, you know, building wine over and over again, trying to get the right configurations to play Guild Wars, this type of stuff. Like that's what I would spend my time doing. And I liked it. Like it was fun. I enjoyed that. I don't know what it was. It was just, you know, sitting there for 30 minutes waiting for wine to compile, kind of fine. So, you know, and then when I actually got to like play the games, like the whole reason you compile wine is so that you can play games slightly faster. All I would do is benchmark the games, put the configurations that I benchmarked the games with on a site online saying that I got slightly better frame rate by using this setup. And then I didn't even play the game afterwards. Me and my pals had Gentoo installation parties in high school. I tried to do something like that as well. Like, okay, so hear me out. When you're in high school, right, you're just starting out college or whatever, like okay, I'm saying you, but I personally did not, I didn't have too many friends that shared my interests, right? And no, that's the thing. When you're in high school, you tend to create your interests, right? Like that's when you start to become interested in things and you become interested in the things your friends were interested in. But the problem was I was friends around the advent of the internet. And so there were a lot of people online who were more interested in stuff I was interested in, you know, like Guild Wars, like, you know, Linux, programming, this type of stuff. And so I found that I was much more friendly. I was much more like connectable. I felt much more honest online than I ever did in person with people. And so for me, I never really had too many of these installation parties, but I did try to create like just a community of people that enjoyed doing this type of stuff. It didn't work out. So like kind of this YouTube channel and the Twitch stream and all this kind of stuff is kind of my way of creating like this sense of community of people that just like to talk about nerdy stuff. And I think it's turned out okay. What do you mean by compiling wine? Just download the exe. Right, so in order to run an exe on any like reasonable modern operating system, you have to download another like kind of, it's called Wine is not an emulator, but you can essentially think of it as an emulator for the exe file. I really wish developers wouldn't write code to use such an outdated format like exe and stuff like that and require what is essentially what is known as a dirty operating system or DOS. It's just that, you know, for some reason, when developers are trying to write things quickly, they tend to just write things in a shoddy fashion, and then they port it to operating systems that don't make sense. So, anyway, too much rambling. I'm so sorry. What do you mean? Just only who needs Cyberpunk 2077 when you can recompile it? When you can recompile, benchmark, and debug your custom kernel? Right. I need CP 2077. I'm sorry, that is an invalid command. CP 2077. You also need to write to where you're copying to. So it's CP 2077, but then you also need like the destination directory. I hope I helped. I'm sorry, I'm an idiot. You should set Gentoo. You should get Gentoo. 5% math ability, 45% randomly, 50% Alabama upbringing. Yeah. I know, I was joking. I'm just being an idiot. Okay, so how are we gonna create this array here? Okay. I have no idea. I'm just dumb. Okay, so we have so it's going to be omega raised to the c. So omega is going to be our base, and it's going to be a primitive. Okay, let's just read this out. The number theoretic transform NTT is obtained by specializing the discrete Fourier transform f is equal to z over p, the integers modulo a prime p. This is a finite field, and primitive nth roots of unity exist whenever n divides p minus 1. So we have p is equal to xn plus 1. Okay, for positive integers xi. Specifically, let omega be a primitive p minus 1th root of unity. Then an nth root of unity alpha can be found by letting alpha is equal to omega xi. Okay. So then they do like kind of a set of operations here. So for p is equal to 5 and alpha is equal to 2, you have 2 to the 1 is 2. 2 to the 2 is 4. And then 2 to the 3 is 3. So why is it modulo 5? I feel like there's a plus 1 in there. Okay, my question is, how do I create this Dft matrix? That's my, or the NTT matrix. I think you need a primitive root mod p. Yeah, I think that's exactly what I need, right? So the primitive root of unity. So, okay, so if we're going to create an array that is, let's say 1024 by 1024, and we want to fill it up with these integers, right? That's what we want to do. We know it has to be mod 5. Oh, no. It has to be mod p. And p is what? So if p is 5, then you're going to create a 4 by 4 matrix, and you're going to do mod 5. Okay, so what you want to do is read in, so p must be the length of the array, and a, what is alpha here? Just a print, size of the finite field. Right, that's what I think it is as well. I think it's the size of the finite field. Because I think n here, which is the size, n equals 4. So when n equals 4, we're using p equals 5. So n, where's n defined up here? I need to figure that one out. Right, no, I understand as a, okay, I'm specifically trying to create the matrix here. So I think the matrix here has like, if you're going to create a 4 by 4 matrix, I think that's the 4 by 4 part of the matrix specifies what your primitive root is. That's what I'm trying to figure out. Like, how do you go from, like, all I want to say is I want the matrix to be 1024 by 1024. And so the question is, how do I pick a root? How do I know what the root is for that value? That's, let's see. So that's my question. I feel you definitely, after all these years, I still can't find people with similar interests. No one around me cares about epigenetic mechanisms or black holes, and sometimes they can't even get the best jokes. Well, if none can understand, it's still a good joke. Is it still a good joke is another philosophical debate out of context. That's true as well. I mean, everyone's kind of a bit weird, and you just kind of work out of that weirdness, or work into that weirdness, depending on the groups that you work with. Hey, a lot of people don't share the same questions I'm asking. They're asking different questions. Most of them are asking already answered questions on Google. Right. Also, who are your... Oh, yeah, that's true as well. Right. So, okay, so it doesn't seem like they have... I think n divides p minus 1. That's what I think as well. So I think that gives us p. So the question is, what gives us alpha? So alpha, is there a relation between alpha and p? There might not be. Which is fine. There doesn't have to be. I'm just trying to make sure. So the Shonhage Strassen algorithm specifically uses a Mersenne number transform. So do we want specifically the Mersenne number transform, which is a variant of? There are phi p minus 1 primitive roots mod p, and alpha can be any one of them. Phi, what's phi? Sorry about that. I'm asking a dumb question. Like, alpha is anything where the power cycle through all non-zero residents resides mod p. Okay, so I guess how to use Google should be an added curriculum in high school. I thought it was in my high school. I wish there was a Wikipedia that has maths and programming notation. Kind of like the algorithm archive if we actually, did that properly. Euler-Tocient function. I don't know what that is. Like 2 is a primitive root mod 5 because 2 squared, 2 cubed, 2 fourth hits all the values of 1, 2, 3, 4 non-zero residents of... Okay, I see what you're saying. So alpha is omega raised to c is what they defined here. So what are omega and c? Oh, that doesn't help at all because omega is a primitive p minus 1. Oh, I gotcha. So c is going to be... Okay, so you can define... I got it. Let's just... I'm going to copy this page, and we're just going to bring it over to Zernal, and we're just going to... Let's just copy this. All right? We're just going to go over here, and we're going to drop it down here. What am I doing with my life? 1 second. I'm bad at this. I need to screenshot. I need to find the screenshot that I just took. It's going to be this one. Perfect. Let's make it a bit bigger so I can just write equations on it. That was my point. I just wanted to write equations on the Wikipedia article. Perfect. All right. So now let's grab this. We'll do pink. Why not? Okay. So what do we have here? This is going to be of size n. All right. And we're going to say that n is going to be equal to p minus 1. I think that's fair. And so now the question is, so if we specify n, then we know p. So if we specify n, we know what p is. That's easy enough. So now the question is, what is alpha? So alpha is going to be equal to omega c, which I can't really write, but pretend I can. And omega is going to be equal to p minus 1. So in this case, I think omega is equal to n. I think, if I've done this correctly. So now the question is, what is xi? And xi is going to be equal to p minus 1 over n, where n root of unity exists, where n divides p minus 1. Okay, so I think I'm doing this kind of okay. So that means that, okay, so this says, this is a finite field and primitive nth roots of unity exist where n divides p minus 1. So p minus 1 in this case is 4. So n in this case could be, okay, I got it. So because 2 is a factor of 4, this works fine. So essentially we chose C to be, no, that doesn't make sense at all. No, this whole thing's wrong. I'm just dumb. Crap. I thought I was getting this, but actually this over here is different. So here they're saying that omega is equal to 2, but omega is going to be a primitive p minus 1th root of unity, but p is 5. What? So omega is a p minus 1th root of unity. Yeah, I'm also a bit confused about this. I think that this isn't as clear as I thought it would be. But I don't know about FFT at all either. Right, so right now we're not worried so much about the FFT. We're just worried about getting the matrix, right? So we're worried about the DFT. So this is a step before the FFT. We're just trying to get the transform right. So, okay. I mean, we can clearly... So omega is going to be a primitive p minus 1th root of unity. Ah, gosh, why is this so confusing? Okay, so the number theoretic transform is obtained by specializing the discrete Fourier transform f onto the integers modulo a prime p. Fair enough. So p is going to be equal to 5, which is going to be equal to n minus 1. So if n is 1024, then p is going to be 1023. And that's totally fine. Okay, so the next question would be, how do you know you're going to do 2 raised to the 2, 3, 4? Like, how do you know this? For a positive integer c. Okay, so I think actually so I think c is actually going to be equal to, one second. I think c is going to be equal to 1, 2, ... n. I think is what this is going to be. Yeah, I think that's what that's going to be. Well, okay, I think you're right. It starts at 0 and then it goes up. So I think that's fine. So that's C. So then omega is the one that we have to choose, and omega is going to be a primitive p minus 1th root of unity. So the question is, why is omega 2 in this case? No, why is alpha 2? So alpha is going to be... I think this article is wrong. See, Trash Talk, thank you so much for coming in. Because I think this should be omega equals 2. When it says alpha is equal to omega. Yeah, this is wrong. What they wrote here is definitely wrong. So if they choose omega to be 2, then your alpha values will be 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. That's totally fine. You need to look up primitive roots mod p. I mean, so then we have specifically let omega be a primitive p minus 1 root of unity. So essentially then you can just choose, right, so essentially you can just choose anything that divides. You can just do anything that divides that, I think. There's no concept of omega or roots of unity in P from what I know. There's no concept of omega or roots of unity in P from what I know. What is P? P is modulo prime P, integers. Let's see. I don't know if I said thanks for following like 20 minutes ago, Julian115, but thank you so much for following. And also C6D2AEC3, thank you so much for following. Really appreciate it. There's no concept of omega or roots of unity in mod P from what I know. Okay, let me just go back over here really quick. See what this one actually says. So modular arithmetic. I understand modular arithmetic. That's not my question. Root. Unity. No. There's no discussion of roots of unity in this. I don't know why the wiki article talks about roots of unity there, or omega at all. I mean the reason's obvious, right? Because the nth root of unity is equal to x, where x, the nth root of unity equals x, where x raised to the n is equal to 1, mod prime p. Oh, no, that's exactly what I needed. Thank you. That makes sense. So, you were saying the nth root of unity, where x squared is x raised to the n. Okay. So you're saying the nth root of unity. So the p minus 1 root of unity is going to be equal to x. So x raised to the p minus 1 is going to be equal to 1 modulo p. I'm not working on the math wiki, but I think that this is wrong. I'm thinking about like just mentioning that their notation is not clear here. Okay, so that means that let me change something really quick. There is file. My eraser is no longer working on this pen and it's really driving me mad. Edit preferences, input system, enable new input system, Wacom, pen cursor, stylus pad, eraser. Huh? How does it not? I'm using the eraser and it doesn't recognize that it's an eraser. Oh, this is broken. The whole thing's broken. That's fine, whatever. What do you mean? What are you saying? I'm going to be nitpicky too and say that omega is bad notation. I think omega is fine notation. I'm just saying that this alpha here, this here is wrong. They said alpha is equal to omega raised to the xi, but xi is 1, 2, 3, 4, and alpha is omega raised to z. So this here is not. They just have the notation wrong here. If they said omega equals 2, that works fine. Okay, so xp minus 1, and you said this is going to be equal to. You said that this is going to be equal to. Where's Jerome's comment? X raised to the n is equal to 1 mod p. So x raised to the p minus 1 is equal to 1. So if p minus 1 is going to be equal to 4, so x raised to the 4 is equal to 1. In mod p arithmetic, there are n different nth roots. Right. There are n different nth roots. In mod 5, all of the 1, 2, 3, 4 are x raised to the 4 is equal to 1 mod 5. 1 raised to the 4, 2 raised to the 4 is equal to 1. Is this true for any? Is this true for any n? So if you have, like, let's say instead of doing, like if you do mod, if you do mod 10, then if you raise any number to mod 9, or if you raise any number to the 9th power, it will give you 1. And the second row is like 1 omega. Yes, I understand that. And the alpha takes on those values 1 at a time, once for each column. And we take all the powers of alpha in the column. Right, yeah, that's exactly what they're doing, no doubt. Totally what they're doing. What I was saying is that alpha is not the correct notation here. Alpha is never equal to 2. That's all I'm saying. So alpha is never equal to 2 in this notation. Alpha is your set of variables in here. In here. So when they say alpha is equal to 2, what they actually meant was omega equals 2, because alpha is equal to omega raised to xc. So here xc is 1, 2, 3, 4. Oh, that's all I was saying. I was saying that their notation here is not correct. Okay. Alpha equals 2 in the second column. Right. That's true. It's equal to 2 here and here. That's true. But is that a notation error or simply a typo? Well, the notation error is a typo. So I think it's the same thing. Sorry, maybe there's a difference between a notation error and a typo, but I think a notation error is a typo. It's just a typo in notation, right? Okay, so I guess my only question is, can you just choose omega to be whatever? Is that actually what you can do? You can just choose omega to be whatever base you want. Because I feel like that's wrong. I don't know why, I just feel like that's wrong. I feel like you should have omega be, or you should have to. So let omega be a primitive p-1 root of unity. And then an nth root of unity alpha can be found, letting alpha is equal to omega raised to the c. Okay, so p-1 root of unity. And you just said there are n p-1 roots of unity. Rather, there are p n-1 roots of unity, Jerungs. There are n different nth roots, right? Yeah. So there are n different nth roots. Maybe I'm not understanding this as well as I thought. Okay, well, good news. We didn't get this implemented today. I'm gonna have to kind of think about this a bit, and how we want to do this. Let me just DD here. I need to read that page a bit more and just kind of figure out what I need. Yeah, I can't even really figure that out. So, okay, here's what we're going to do. We're going to call it for today. We're going to come back, not tomorrow. Again, I have something to do tomorrow, but I'm going to use the spare time I'm not streaming tomorrow to read through that and try to figure out what this means. I'm sorry. I know I'm dumb. I'm sure people are probably going to comment on Discord saying that, clearly, there are better ways to understand this. Only some roots of unity are primitive, like only the relatively prime ones. Right. So I think what I need to do is learn more about roots of unity. So I think what I'm going to do is I'm going to Google that. Actually, this might be super helpful. Yeah, this actually might be what I want. Okay, so what is this? This is saying the number theoretic transform is a generalization of the classic DFT to finite fields. With a lot of work, it basically lets one perform fast convolutions on integer sequences without any round-off errors guaranteed. Convolutions are useful for multiplying large numbers or long polynomials, and NTT is asymptotically faster than other methods like Karatsuba. Let's go through this on Wednesday. I think this is what we want to go through. This is it. I think this should be it. This will help us. This is our saving grace. I'm just going to go ahead and put that on our bookmarks, and we're going to go through that on Wednesday. And in the meantime, I'm going to read up about roots of unity, because clearly I don't know what I'm talking about. The thing is, it's so easy in principle, right? A root of unity is just anything that square root is 1, right? That's all it is. So that means that, in complex spaces, just anything on the unit circle is a root of unity. So this, I think, is why I got so confused. I guess in my hubris here or whatever, I kind of thought that, it'd be super simple, because all it is just, square root it, you get 1. But when you start talking about, no, not square root of 1, but x equals square root of 1. What? The important thing for NTT is primitive roots, not primitive roots of unity. All x such that x squared is equal to 1. I think they're saying primitive roots of unity, because roots of unity is how you typically define the DFT. And so because it's in the discrete Fourier transform, like it's on the page for the discrete Fourier transform, they're specifically talking about them as roots of unity. All x such that x squared equals 1. Oh, that's correct. Yeah. Yeah, that is correct. Yeah, I said that wrong. Hey, KMac 0707. Okay, so I think this is a good place to stop for now. We have an idea of what we don't know. That took a while. I did a lot of rambling today. I do apologize for that. Less rambling on Wednesday. I promise we'll do more math on Wednesday. People might be either more or less excited about that. Let's see who is live and who we want to raid at the end of stream. We've got Kitboga. Hello, Mayuko. Strager. You know what, guys? Hear me out here. Hear me out. I'm a big fan of Kitboga's stream. I say we raid Kitboga. I realize, look, I know I should be supporting smaller streamers. That's what I should be doing. But also, like, big fan of Kitboga's stream. I am trying, like really trying to like get a big enough audience that eventually Kitboga's like, hey, let's do a dual stream together. And I really want to do that at some point. It's one of my Twitch goals. I don't have too many goals for Twitch, but one of my Twitch goals is to do a pair stream with Kitboga at some point, because I'm a big fan of his channel. So we're going to raid Kitboga. You guys are going to have to deal with it. I'm sorry about that. Naysayer88. Am I following them? I'm not, but I feel like I am. Anyway. It's easy. Stop streaming to a dead category and then you'll blow up. Yeah, okay. I'm against doing that as well. I'm not going to stream on just chatting. I think just chatting is wrong. This is the thing that really, it actually kind of pisses me off a little bit. And I've been doing too much rambling today, but whatever. The point is, I genuinely like science and tech content. It's basically the only type of content I watch on Twitch, science and tech and art. I do not watch just chatting. But the problem is a lot of the really good science and tech streamers leave science and tech and go to just chatting. And so I feel like, if we're going to do this, let's do it. Let's just own that we're in science and tech and just, that's where we are. Again, I don't care so much about growth on Twitch as much as I care about growth on YouTube. And I genuinely feel like at some point, hopefully the YouTube channel grows up and that allows the Twitch channel to grow up as well. And in doing so, we get the science and tech category up a couple ranks. Like that's where I'm at. 12,000 people don't want to watch DFT content. Yeah, that's probably true as well. I mean, unless it's 3 Blue 1 Brown doing DFT content. It's actually nice. It's nice to actually talk to people when you have less than 100 viewers. 1,200 people watch auto code though. It's possible. Yeah. Anyway, I'm gonna go for now. I'm gonna start the raid on Kitboga. Raid Kitboga. And that is it for today. So anyway, guys, thank you so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you guys around next time for the next episode of Simuleos. KMac 0707. Thank you so much for following. And I will see you guys next time. Bye, guys.